5 factors of soil formation and parent material. There's the climate, there is the topography, you have the biology of the system, and you also have time. So the idea of the exercise today really is to have a look at the soils along the classic Catena sequence in North Wales, which runs right from the coast here all the way up to the mountain tops. And essentially the Catena sequence is an altitudinal sequence of soils which, basically as you go up in altitude you have changes in climate, but also changes in geology, which causes the changes in the topography itself. So this Catena sequence has a classic 5 factors of soil formation which changes as we go along from the low level here, from the coastline right up to the mountain top, and we'll be able to see essentially how that shaped the soils that we see before us. And here we are right at zero, ground zero really, and this is a very young soil. It's an Entisol, and it's a characteristic soil of the start of soil formation. And the reason that we say that is that we know here that this soil, in contrast to most sites around the UK which are post-glacial in the sense that they're all about 10,000 years old, this site is actually quite young because it's receiving sediments from the sea, and it's basically the gradual build-up and erosion, that progressive sequence of events over time that's led to the deposition of all of this silt material that we can see here. So if you can tell it's silt material because when you rub it between your fingers here, you can feel that it's got that soapy feeling to it. So it's a deposition of silt progressively over time, and shell material. You can see in the soil profile here this sort of white material that's led to this soil. And the classic feature of an Entisol, of course, is that it doesn't have any soil horizons. And what I mean by that is that when we look at it here, you can't really see many distinct soil layers. There's the startings of one about here where we've got more organic material at the top, which will head us into an Entisol at some point in the next few hundred years. So in terms of the 5 factors of soil formation that we use to characterise all of the soils of the UK, we can say that in terms of time, this soil is quite young. It's maybe 200 years old. In terms of the vegetation, one of the classic features here is that we have this unique biodiversity, this sort of what we would call a halophytic community, one that really likes salt because occasionally this site gets covered with seawater, and that gives rise to a high salt content in the soil but also a high soil pH. So we're selecting for this unique biodiversity here. In terms of topography, it's a very flat site here. We're down at virtually sea level, and it's a classic flat site which is eroding soil material not through gravity but just through the depositional events. In terms of the climate, we are on the lowlands here, so we're talking about 1,000 millimetres of rain per year, so quite low relative for the compared to the uplands. And we have a mean annual temperature of about 10 degrees centigrade. So this soil never ever freezes. It's under very rare circumstances does it freeze. So it's active all year round. And in terms of the parent material, well, classically it's this silt material, which is from the ocean floor, which is washing up, but also erosion we've got the local river here, in the River Aber, which is depositing silt material, bringing it from the uplands and then washing up onto the shoreline here. So that sort of characterises the 5 factors of soil formation. One of the characteristic features of this soil that we can tell by its colour relates to the moisture content of the soil, so the amount of water it holds. And we can see here, just from where my feet are, that the water table is quite high. And this theta probe here basically measures the amount of the water that's in the soil profile. So if we put this into the soil profile and we take a measurement of the soil water content, it's giving a measurement of about 40% water content. So 40% of the soil volume is made up of water. Well, 50% is made up of mineral material here, and the other 10% is air. Now, for a perfect soil, really what we want is 25% air, 25% water, and 50% mineral material. So this has got too much water in it. So that has led to the fact that with a really poor soil structure, so that's the way that the particles are arranged together rather than the texture, which is the sand, silt, clay content, you can see it has no structure. So what I mean there is we don't have any pore space here, particularly any cracks in the soil profile that we can see. So this is very waterlogged, particularly in the winter and when the tides come in, of course. And that leads to anaerobic conditions prevailing in the soil, which gives us, it means that the iron in the soil gets reduced by the microorganisms from iron 3+ to iron 2+, and iron 3+ is red and iron 2+ is a grey-green colour. So what we're looking at here is we can see the brown colour from organic matter, but one of the other classic features that we can see in this soil is it also has black hydrogen sulfide and iron sulfide accumulating here from the anaerobic conditions, and we can also see that it has some sort of reddish spots where the roots are putting oxygen, pumping oxygen into the soil, but mainly around those we can see that the soil is completely anaerobic. If you smell the soil, you can smell it's emitting hydrogen sulfide, and that's partly because of the marine water that comes in here, which is really high in sulfate. So one of the diagnostic soil quality indicators that we normally measure when we come to a soil profile is the pH and the electrical conductivity, and that gives us an idea of, from pH you can infer lots of things about nutrient availability, for example, but also if you measure the electrical conductivity, it gives us a measure of the salt content and whether that's a constraint for plant production, for example. So it's really easy to do, and it's definitely worth doing if you have the time. So I've just got a tube here. I'm going to take some soil from the soil profile, about 10 centimeters cubed. I'm going to put it in this tube here, as we can see, and I'm then going to just add some distilled water here from my bottle. And the idea is that the distilled water will equilibrate with the soil, and we'll get an idea about the chemistry of the soil based on the pH and the electrical conductivity. So just put that to one side, and then normally we would shake this up for a few minutes, but in the interests of time really, I've got one here that I prepared earlier, so we'll just put this to one side, leave that to settle if we wanted to do a second replicate. But here's the soil with the distilled water that's been shaken up. You can see now it's a nice suspension. The soil is well mixed with the distilled water, and we can just take the lid off. And here I have the electrical conductivity meter. So this has got 2 platinum electrodes in it, which is essentially measuring the amount of ion or electricity that's conducted between the 2 electrodes, and the amount of salt and ions that you have there means the more electricity can pass. So if we test the water here, and this is pretty close to what seawater would be, so here it's still moving up a bit, 50 millisiemens per centimetre. So, and we'll see how that contrasts with other soils in the Catena sequence as we go along. Clearly that is the groundwater, and it's slightly different because that's at the bottom of the soil profile. And what we're going to do now is just check the soil itself and see how it compares. So I've put my electrode into the solution here, and I'm just going to measure it off. And we can see that here the soil is 8.5 millisiemens per centimetre. So in terms of plant production or something, the critical value is about 2 millisiemens per centimetre. So above 2, you can't really grow crops. So the salt is too toxic. So here, it gives us pretty good evidence that we have salt is a major issue, and hence why these plants that grow here are super adapted. And the other thing that we're going to measure is the soil pH. So of course pH is on a log scale, and we're looking for normal soil pHs go from around 3.5 to about pH 9 at the other extreme. And perfect pH for plant growth really is about 6.5, which is why in agriculture we always lime to that amount. So here I've just put my pH electrode in, and we're watching now the pH move up. So it takes a little while to settle in this soil, because of the calcium carbonate buffering. But generally what we're seeing here is that the pH is rising steadily and it's going well above 7. And what that's telling us really is that the pH is really high. Essentially, when we have really high pHs, we have micronutrient deficiencies. So it means that the copper, the zinc, the manganese, those essential nutrients for plant growth, are becoming limiting, because as the pH goes up, the level of those micronutrients in the soil becomes more unavailable. They're still there in the soil, but it's just they're really insoluble and it's difficult for plants to get them. And the other extreme, of course, is acid soils, which we'll see later on, where those micronutrients are available, but we have other toxic metals that become more soluble in the soils.